Hello everyone, welcome back after a very long time. Hope you all are safe and fine, and you all are enjoying this unwanted vacation, staying at home. Um, Now coming to the issues. Today I am here because I have a topic from your syllabus to discuss with you, and the topic is from electrodynamics, uh, electromagnetic wave in bounded media. We have already discussed, we have been discussing on this topic of electrodynamics since one last month or so. We have talked about it a lot in previous classes, especially on the basic laws of electrodynamics, and then we have forwarded this discussion on the behavior of electromagnetic wave, or specifically the behavior of electric field and magnetic field and their interaction and propagation in an unbounded medium. And we have discussed the behavior of electromagnetic wave in free space, dielectric, conductor, or some ionized medium like plasma in previous classes. But we also talked a little about the behavior of electric field and magnetic field when the electromagnetic wave reaches the boundary of two different media. That means here boundary of two different media refers to the boundary of two different dielectric with different dielectric constant, or it may be dielectric conductor boundary, or it may be free space dielectric boundary, or it may be conductor boundary with different conductivity, or there may be several other cases, and we have discussed it in broad way in previous classes. Now today we shall continue this topic or idea of electromagnetic theory, and we will use the basic laws of electrodynamics to study the laws of study the manner of or behavior of electromagnetic wave in the boundary of two different media in more details. So I am very sure that we are here after a very long interval, so you may have forgotten the previous knowledge and the equations you have derived in previous discussions. So I have to recapitulate the equations and the ideas which we have already derived in recent pasts. You all know that the basics of electrodynamics is based on the electrostatics and magnetostatics and their mutual interaction. We have started the topic from Coulomb's law, then derived Gauss's law, and then we have studied the magnetism through Biot-Savart law, and then we have studied the Lorentz magnetic force law and Ampere circuital law, and these all laws of electrostatics and magnetostatics after some magnification is assembled by Maxwell, and he constructed the laws of electrodynamics, namely Maxwell equations. So to study the further proceeding, we shall have to do some knowledge, and we have to do some derivation on Maxwell equations. So we know that we are starting with the Maxwell equations. We all know that the contravariant form of Maxwell equations in tensor format will be written as del mu f mu nu is equal to j nu, and this m mu nu is nothing but the electromagnetic field tensor and is given by del mu a nu minus del nu a mu, where a mu is electromagnetic 4 potential, and the components of this tensor will be the time component is a0, that means volume charge density is rho, and other three component is magnetic vector potential. The time component of this electromagnetic potential 4 potential is electric scalar potential, that is phi. This is the time component of a mu, and other three components are magnetic vector potential magnetic vector potential A. And this J nu is nothing but current density, 4 current density, and the components are, first component is the J0, which is nothing but the volume charge density rho, and the other 3 component is JH, that means Jx, Jy, Jz. So that's the contravariant form of Maxwell equations. And this Maxwell equation can be written in a broad way, that the first Maxwell equation, which is nothing but Gauss's law, and this Gauss's law, the differential form of Gauss's law can be written as divergence of E, that means divergence of the electric field is given by rho by epsilon 0, where rho is the volume charge density. Now let us consider the dielectric medium. For a dielectric medium, under the external electric field, the molecular dipole tends to be aligned along the direction of the external electric field E, and thus polarization occurs. And due to this polarization, bound charge arises within the substance, and these bound charges can be distributed in two different way of distribution. It can be like a volume charge distribution, and it can be like surface charge distribution. So this bound charge yields rho b, that means volume bound volume charge density, and also it may yield the surface bound charge density sigma b. So for dielectrics it yield bound charges two different way of distribution, two different distribution of bound charges, rho b and sigma b. This volume bound charge distribution depends on the nature of polarization within the interior of the dielectrics. That means if the polarization be uniform or homogeneous, or then the polarization vector B is constant, then this rho B may be 0. So there should be no bound volume charge within the substance. But if there exists some gradient of this polarization, then there exists the bound volume charge. Similarly, the surface bound charge depend on the normal component of the polarization along the normal directions of the substance, normal direction of the surface enclosed by the substance. So we know that the relation indicating the value of rho b and sigma b is rho b is equal to minus divergence of P, where P is the polarization vector and sigma b is equal to P dot n cap, and we all know that P is equal to the net dipole moment per unit volume of the substance. And you all are aware of the fact and aware of this expression, and you have studied it before in previous classes. Now clearly rho for a dielectric can be written as rho b plus rho f, and putting the value of rho b in this expression, and it is used in the Gauss's law, general Gauss's law, divergence of E equal to rho by epsilon 0. It can be written that divergence of epsilon 0 E plus P is equal to rho f, and this term can be written as electric displacement vector divergence of D equals to rho f, where D is equal to epsilon 0 E plus P, and we all know that P is proportional to the external electric field, and the proportionality constant can be written as epsilon 0 chi, where chi is the electric susceptibility. So it can be written as epsilon 0 into 1 plus chi multiplied with external electric field E, and 1 plus chi is actually equal to the relative permittivity epsilon r. So epsilon 0 epsilon r into E, and it is equal to epsilon E. So this is the Gauss's law for dielectrics, and it is the first Maxwell equation. And the second Maxwell equation, and it is very well known equation, but it has no specific name, and it arises due to the inexistence of magnetic monopole. So the inexistence of magnetic monopole, that means all magnetic interaction starts minimum from the dipole term. So the net magnetic induction flux or the net flux of magnetic field vector V will always be 0. That means B dot n cap ds over any closed surface S equal to 0, which leads divergence of B will equal to 0. So it is the second Maxwell equation, and the third Maxwell equation, which is nothing but the mutual interaction between electric and magnetic field. It indicates that a moving magnetic field, that means a moving magnetic flux, can generate the electric field, and it is called the induction. And this theory of induction actually introduced by Faraday. So this law was known as Faraday law. Later, Lenz just modified this equation by introducing the idea of direction of the electric field in a closed contour, and he just introduced the theory as curl E is equal to minus del B by del T. This minus is introduced by Lenz. Faraday did not introduce this minus sign, and this minus sign actually denotes the direction of the electric field, and the direction of the electric field will be such that the current generated due to electric field will oppose the causes of this electric current, and it was also discussed before, and you have a better realization on the equation. And number 4, the equation is which is known as the Ampere circuital law, and it can be written as curl H, and it is curl H equal to JF, which is free volume current density, plus del D by del T. So this is the 4 Maxwell equation, and you are very well familiar with these 4 equations, and it is called Maxwell equations. Now based on this 4 Maxwell equation, we have studied the nature of E and B, H and D within an unbounded media. That means interior of a single medium, in a homogeneous medium, where the property of the medium is same in every space or every point on the medium. So it is called the unbounded medium, where the properties of the medium are same. So we have discussed the nature and manner of electric field and magnetic field, and their interaction and propagation within such unbounded medium. And we have discussed it before many times. Now we are interested, and we are going to discuss about the behavior or manner. That means how an electromagnetic wave can behave when it comes to the interface of two different medium. That means the boundary of two different medium, where the boundary can be taken as dielectric boundary with different dielectric constant, or the boundary of two different conductor with different conductivity, and a dielectric conductor boundary. It may be free space dielectric boundary, or etc. Different type of several case may be studied, and it has been studied before a lot of time, and you are very aware of this analysis which was done before. And applying these 4 Maxwell equations at the boundary of two different medium, we can find the boundary conditions. That means the conditions of continuity or discontinuity of these 4 fields, that means E, D, V and H. And we have done it before, at least 2 times I have shown it before you. And the boundary conditions are we can easily find out by applying this force law, and considering a Gaussian pillbox, that means Gaussian cylindrical surface at the boundary, and applying first to Maxwell equation, divergence of D equals to rho f and divergence of B is equals to 0, over that closed Gaussian pillbox, we can find the conditions d2n minus d1n is equal to sigma f. That means the normal component of electric displacement vector is not continuous at the boundary, and the difference of normal component of electric displacement vector between two different medium or two different dielectric medium with different dielectric constant is equal to the free surface charge density at the boundary of two different medium. Similarly, divergence of B equals to 0, it yields that B2n minus B1n is equal to 0. But rather the magnetic field, the normal component of magnetic induction field B is continuous at the boundary of two different dielectric medium. And then we may consider a closed contour or closed rectangular contour at the boundary surface of two different dielectric medium with different dielectric constant, and we can show that this actually yields that the tangential component of electric field E and auxiliary field H yields E2t minus E1t is equal to 0. Similarly, H2t minus H1t is equal to Kf, where Kf is the free surface current density of the medium, free surface current density of the at the boundary of two different medium. Now that is the general boundary conditions at the boundary of two different dielectric medium. Especially we are going to discuss or going to talk more about the boundary of two different dielectric medium with different dielectric constant. Now if we consider the boundary such that there is no free source present at the boundary, that means the boundary of two different medium is sourceless, that means chargeless and currentless. So we can here introducing the fact that we have a consideration, or we may assume the surface be such that sigma f is equal to 0 and kf is equal to 0. So under such boundary, that means we have considered such a boundary where no source is given, then the boundary conditions can have been written in the form that all the components, normal components and tangential components of E, B, D, H, all are continuous, all will be continuous. Then we can write D2n is equals to D1n and B2n is equals to B1n, E2t is equal to E1t, and H2t is equal to H1t. So it is very, very clear, and it is not too much difficult to realize or understand the fact. So it's a very simple calculation, and expect you all get it very rightly. Okay. Now since our school life knowledge, that means the knowledge from the textbook of our school life, even from the secondary level, we are very much familiar with the fact that when an electromagnetic wave, and rather you are then familiar not with electromagnetic wave much, you just mention it a light. So when electromagnetic wave or light comes to the boundary of two different medium, and let us consider this boundary be a plane surface, that means the boundary of two different dielectric medium here considered as different dielectric constant is such that the boundary is a plane surface. So when a electromagnetic wave or light comes to the plane boundary of two different dielectric medium with different dielectric constant K1 and K2, there may be two well-known phenomena. One is reflection and another is refraction. So it is very well known phenomena, and you all are aware of this phenomena of light, and you have studied it in secondary level, also in HS level, and also in the previous semesters like optics in this graduation courses. So it is a very well known these are the very well known phenomena, but our aim is to estimate the well known theory of reflection and refraction, which we have studied before in optics. uh, mm, we have to estimate this well known theory of reflection and refraction from the electromagnetic theory of light, and which we have been studying since one last month or so. And that's the scheme of this class. The scheme of this class is to uh, prove or derive or estimate the laws of reflection and refraction from the theory of electromagnetism. Now just quickly highlight on the laws of reflection and refraction, and you all know that the laws of reflection suggest that the reflected wave, the incident wave, that means the electromagnetic wave which are incident on the boundary of two different wave, which called the incident wave, and the reflected wave, and also the outer normal at the point of incident from over the reflector surface is in the same plane, and this plane is called the uh, plane of incidence. So there exists a plane of incidence while reflection. It is the first law of reflection. And the second law of reflection is that the angle of incidence is equal to the angle of reflection. That means the angle of incidence refers to the incident wave, the angle made by the incident wave with the outward normal from the reflector surface. Similarly, the angle of reflection is defined as the angle created by the reflected wave with the outward normal to the reflector surface. And as per the laws of reflection, these two angles are same. And if we consider, or if we want to highlight the laws of refraction, it suggests that similarly there should be some plane of incidence for the refraction. That means the incident wave, refracted wave, and the outward normal will be in the same plane. And the second law, which is well known as Snell's law, and the multiplication of the refractive index of any medium and the angle is constant. That means n1 sin theta 1 is equal to n2 sin theta 2. So that's the well-known theories or equations of reflection and refraction, which we have already studied in the optics. Now just we want to establish the theory. So consider the figure that is, suppose it is the boundary, and the cross section is drawn here because it is the plane, boundary plane. That means it is in xy plane, and this is z direction. It is z direction. It is suppose in xy plane. So it is the boundary plane or plane boundary of two different media, rather two different dielectric medium, and it is the dielectric medium, first dielectric medium with the dielectric constant, suppose K1, and it is the second dielectric medium with the dielectric constant K2. Suppose an electromagnetic wave is coming out and be incident on that point O. So this is the incident wave, and then reflection occurs. So it is reflected wave, and some part of this incident wave be transmitted through the second medium, and it is the transmitted wave. Okay, so it is a very well-known picture to you, and this angle is defined as the angle of incidence, and I denote it as theta I. And this is the angle of reflection, this is theta r, and this is the angle of refraction or angle of transmission, this is theta t. So it is very easy to understand this figure, and as you all know from our from our secondary level, this phenomena occurs when electromagnetic wave is electromagnetic wave comes to the boundary of two different medium with different dielectric constant K1 and K2. K1 and K2. So now we are going to establish the theory of reflection and reflection, just applying the laws of electrodynamics. Okay. Here we just apply the conditions that the tangential component of electric field of electromagnetic wave will be continuous at the boundary, and it will be continuous at any point on the boundary at any instant of time. That means the tangential component of electric field of two different media will be continuous at the boundary, and it will be satisfied in all points lying on the boundary and at any instant of time. So it is the condition of continuity of tangential component of